have to speak a lot louder. Yeah, we can't hear a word back there. So it's a mic.
Right, so we hope.
Come past the camera. Like, go down. No. Okay. Good.
Okay. So this is joint work with Bill, and our goal is in these 3 lectures to describe our work on embedded minimal disks. So this is the key for studying minimal surfaces of a given fixed genus in a fixed arbitrary tree manifold. And what we hope to do is, by restricting it to just discussing embedded minimal disks, we hope to be able to outline some of the main idea in this work. So I want to start just with a couple of simple examples. Of embedded minimal disks. So the first example is a minimal graph. So this is a minimal graph. And so a minimal graph is that you're looking at a function u defined on some domain in R2. This domain is simply connected. And so this is a function on such a domain, and this function satisfies the minimal surface equation. So it satisfies the minimal surface equation, which is the equation divergence grad of u divided by the square root of 1 plus the norm of grad u squared equal to 0. Right, so you're looking at the graph of such a function. Right, so the graph of u, right, is an example of an embedded minimal disk. So that's one example. A more interesting example is a helicoid or a piece of a helicoid. Example 2 is a helicoid. Or you could look at just a piece of it, and by a piece of it, I mean intersect the helicoid with a ball is the ball in R3. So, right, so you're looking, so the helicoid, right, is the minimal surface, which has a parameterization cosine t, sine t, times t, so it's this helix, and then there's a line through each point. So S and T are in R. Right, so the way to think about the helicoid is that you have an axis, and then you rotate a line around this axis as you're moving up the line. So this gives you the helicoid, which is this ruled surface. And so the helicoid, if you think about it like that, then you see that the helicoid is like a double spiral staircase. Right, and it's really like a double spiral staircase, meaning that one person could go up the staircase and another one could go down, and they would not necessarily meet if they went on different staircases. Right now, so this is sort of the 2 main examples, and our main theorem, which I just will describe loosely now, and then come back to later. So the main theorem is like this, that every embedded minimal disk in R3 can either be modeled by a minimal graph, formed by the helicoid or piece of helicoid, formed by, I'll just say the helicoid. And this is so you model it by a graph. This is if the curvature is small, then it's modeled by a graph, and if the curvature at some point gets large, then the model is a helicoid. So model means right. So I don't. Okay, I wasn't going to state it. Let me state it a little more precisely. We just write depending on whether the curvature at some point, or whether there is a point of large curvature, maybe I should say it, whether there is a point of large curvature. Curvature and large curvature. Okay, so let me say a couple of words then about what I mean by models. So the way we think about this is that we have, suppose you have a sequence of embedded minimal disks. Let's say in some ball, and let's say it's a ball. Right, again, if we use the notation like this here is a ball of radius r and center. If it doesn't have a center, then understood at the center is the origin. So suppose you have a sequence of embedded minimal disks. Well, if these embedded minimal disks, right, were, so if you're looking at, if you have here the helicoid, right, suppose you're looking at the helicoid, we have this double spiral staircase like this, right, through these lines. So if you take the helicoid and now you rescale, so you're looking at a sequence of rescaled helicoids where you multiply it by 1 over I, the helicoid, and then you let I go to infinity. Right? Then you get a sequence of, so then this here gives you a sequence of embedded minimal disk, and the curvature is actually blowing up, right? So this is this gives you so this is give you so this gives a sequence of embedded minimal disk with curvature going up. Right now, if you're looking at this double spiral staircase and you rescale it, right, all that happens is that the rotation, as you think about that you're rotating this line along an axis, it's just like rotating the line faster and faster as you're moving up, right? And in a limit, right, you get, so the curvature is blowing up, but it's really just blowing up along this vertical axis that you're rotating around. And in the limit, right, you get this foliation. So this here is the limit where you get a foliation y flat parallel planes. Right. So that's how the helicoid look at, and that's how rescalings of the sequence, rescalings of the helicoid look like. So now, what I mean by modeling is that if you have a sequence of embedded minimal disks in our tree, and let's just say, for simplicity, that these here are embedded in balls where the radius of the ball goes to infinity, then we get the same picture. So we get that if the curvature is blowing up, just like it does if you're looking at a sequence of the scaled helicoid, where this I go to infinity, right, then the curvature blow up along at a point. In fact, it blow up along a whole axis, right, this X3 axis. Right? And so the main theorem is that if you have a sequence of embedded minimal disks, and if the curvature is blowing up at some point or in some compact set, then there is a subsequence and a curve, a Lipschitz curve, just like this axis here. So that if you remove this curve, then each of the surfaces in the subsequence breaks into two multivariate graphs, and they are connected along this axis. And in the limit, all you get is a foliation of parallel planes. Right, so I'm going to go into much more what all this means, but that's sort of that's in words the main thing. Right, so I want to actually start making some of this precise right away, and so I want to talk about first. Right, so this is sort of a way of describing the helicoid. So the way to describe the helicoid is through multivariate graph. Right, so I want to have a precise notion of what we mean by multivariate graph. Right, and again, the idea is that if you take a helicoid, you remove the X3 axis, right, then this should break into two multivariate graphs, right? These two spiral staircases. So multivariate graph, by we define as this, sort of the obvious way that you take the complex plane, you remove the origin, and you're looking at the universal cover of this space. And we call this strip P. And here we use global polar coordinates, rho, comma, theta. And so rho, right, is positive, and theta is now, since it's on the universal cover, theta is allowed to be any real number. I should say actually here that I'm going to distinguish between multivariate graphs and graphs. So these are going to be two different things. And this is just because our multivariate graph doesn't close up. As they come back, they either go above themselves, where they were before, or they go below themselves. So multivariate graph is not going to close up. So now, right, so we have to define a multivariate graph by looking at the universal cover of the complex plane with the origin removed, and then an invariant graph. So an invariant graph, so n is some integer. An invariant graph is a single value graph. So an invariant graph, let's say, over an annulus. So this is an annulus going from there. So this is an annulus in the plane. E is the disk. So it's an annulus with inner radius R and outer radius S. This is S and this is R. This is So an invariant graph over such a region, such an annulus, is a single value graph over, right, and now it's just over the domain in this domain in this P, where rho lies between little r and and S, and theta is bounded in absolute value by pi times n. Right, so that's an n-value graph, right, and n is always going to be greater or equal to 2. Right? And again, the n-value graph we are interested in will be embedded, so we will restrict to embedded graphs, embedded multivariate graphs. Right, so now there's a sort of useful way of thinking about embedded or multivariate graph is that you're looking at the separation, so you define the separation of a multivariate graph. Right, so suppose you have a multivariate graph defined of a function u, then the separation is just, right, so you have this multivariate graph, it's just the difference in height as you come up back one sheet above the previous sheet. There's a difference in height. So this here is the separation. And so the separation is this function w, which in these polar coordinates, right, is the difference in height, right? So the difference in height is u of rho theta plus 2 pi minus u of rho comma theta, right? This here is the value at rho comma theta, and this here is the value at rho comma theta plus 2 pi. Right, so the separation is just the height difference. And so now you could think about, just in terms of this function, like all embeddedness means is, so embeddedness just means that this function, so embeddedness means that this function w never vanishes, right? That it either comes back continuously above itself, or it keeps coming back below itself and then further down and further down. So it's either spiraling up or spiraling down. This here is, so if this is positive, then it's like spiraling up. And if W is negative, then it is spiraling down. Now, let's just test this in the case of the helicoid. So, right, so again, in the helicoid, right, was this, remember the helicoid? It had the parameterization cosine t, sine t, and then times s. Where S and T are in all. This is sigma. So now, if you take sigma here and you remove the x3 axis, right, so this is of course where S is equal to 0. Right. If you remove the x3 axis, then this here breaks into two infinite value graphs. These here are infinite value graphs. And you see that by this t here, right, if you use these global polar coordinates, right, then t is exactly theta, right? So t is exactly theta, and s is actually either rho. This is in case where it is positive, and in case where it's negative, then it is like it's minus. It's like s equal to but actually it's like, right, so it's either, in fact it's like, one of them is T is equal to theta and S is equal to rho, and the other case it is like T is equal to theta plus pi. So you see that these two infinite value graphs are graphed over a function. One is over the function u1 equal to theta, and the other one is a graph over the function u2 equal to theta plus pi. And so you see that in either case, of course, so in either case, for either of these two multivariate graphs, the separation W is actually constant, equal to 2 pi. Right? So this is sort of the way of thinking about multivariate graphs. And of course for us, the interests are in embedded multivariate graphs. So it was either spiraling up or it was spiraling down. And of course also our multivariate graph will be minimal. So it would satisfy our function u, so our multivariate graph. Will be minimal. So u will satisfy the minimal surface equation. Okay. So now what I want to start with is a little sort of analysis of multivariate graphs. So multivariate embedded, multivariate minimal graphs. So what can we say about these? And this is results that are then going to be used later on. And so the idea is I'll do that today and see how far I get. And then Bill tomorrow will talk about how do you get these multivariate graphs in the first place. How do you, if you have an embedded minimal disk, how do you construct in that? How do you construct a multivariate graph? Okay, so now the first, which I'll just mention, the first result on these is that the curvature decay faster than quadratic. So if you have an embedded, so for an embedded double valued minimal graph, the curvature decays faster than quadratic. Right, so this means that suppose that you have that this here is a double value minimal graph, embedded minimal graph. And let's say that it's defined on an annulus. I just want to rescale the annulus so that it starts off at 1, just for simplicity. Then that it's decay faster than quadratic. Here I mean a power faster than quadratic. So it is that the second fundamental form squared, right, which up to a constant 2, minus 2, which is the same as the curvature, that this here decays faster than quadratic, which means that this is bounded by some constant, universal constant times rho to the power minus 2 minus 2 epsilon squared. So this requires some slight condition on the double value graph in terms of the separation along the slit. But for us, this condition will always be satisfied. And the one for these multivariate graphs that Bill will discuss how to construct tomorrow. Right, and so this here, to prove this, I require that you use just like in the Bernstein theorem, you need to use the nonlinearity of the equation. Right, this here, of course, also uses this nonlinearity in the equation. The next couple of things I want to mention does not use the nonlinearity, but it's more illusions. So, right, so the next theorem I want to mention and I want to outline the proof of is about the growth and decay of the separation. So this is the following theorem. And suppose that sigma is an infinite value. So I just stated for an infinite values graph, minimal graph. It then can be seen to hold not just if it's infinite value, but if the number of sheets as you go out grows sufficiently fast. And that's actually crucial, that you are allowed to just have a growing number of sheets. Anyway, but I'll just state it for infinite value graph. So suppose that this is an infinite value embedded minimal graph. And let's say that it's defined over some region, over some angles. And again, I just want to start off, let's even go out to infinity. So I just want to start off at 1, just for simplicity of notation. So if this is the case, then what you get is that, let's call it maybe a proposition, is that if you're looking at the separation as you go out, so you have here, your multivariate graph. This is your double variate graph, and then you go out. So if you go out now, so the theorem saying that if you go out where theta is equal to 0, and you're looking at how does the separation change as you go out. So what is the separation between this sheet and the sheet above as you go out? Then the proposition here saying that this separation, it grows at most logarithmically, and it decays at most logarithmically. So there exists two universal constants, C1 and C2, so that it's bounded from above and below by above by log of rho and above by 1 over log, or below by 1 over log. This is like an upper and lower bound for the growth of the separation.
What's the term in the middle? W1, 0?
This is this here, sorry, you're right. Here I wanted the 2. I wanted to come in just a little bit. So I want to, this here, I want to look at it starting at this point here. I want to compare to what is the separation here. I want to compare the separation further out to what it is here. And the thing is that this sort of profile curve might be the worst that can happen is that it's k logarithmically, and the best that can happen, maybe we'll explain later why this is the worst and the best, is that it could grow logarithmically. So this is, so I want to just outline, if you will outline this very quickly, why this here should be the case. Right, and again, so Right, so to do that, I'm going to need this here. Right, this here, again, uses the nonlinearity in the equation. Yeah. C is just a universal constant, right? There is some slight condition on the decay, actually on the growth of the separation along the slit. This is like a sublinear growth along the slit. This is always satisfied. We'll probably talk about this, that is always going to be satisfied in the multivariate graph that we will look at. And so this is then some universal constant. Epsilon is also universal, and it's actually, I think it's -5/6. Well, it's actually, it's 2 epsilon. It's 5/6 or something. In any case, it's not sharp. These things are not sharp. The important point, you'll see in just a second why it is important that this here is faster than quadratic, and that's all we care about. So the idea is, right, so this here uses the nonlinearity. This here, the nonlinearity of the minimal surface equation. Of the minimal surface equation. And again, the next thing doesn't use it, but it doesn't use the nonlinearity, but then it uses this to say that we can actually model the minimal surface equation by the Laplacian equation. Right, so this is sort of, for some things, right, the minimal surface equation really gives you more than if you had something satisfying a linear equation like the Laplacian equation. For other things, it doesn't seem to give you more, but it's like illusions. Okay, so now, right now, for these other things, the idea is that if you're looking at a minimal surface equation, right, this is fairly close to the Laplacian equation, right? And as the gradient of the function becomes smaller, then this here becomes more constant. The denominator becomes basically constant. And so it should somehow be closer to the Laplacian equation. And so what this here allows you to is, so this bound here by the second fundamental form up to a constant is basically just is bounded above and below by the Hessian of the function squared. Right, so it gives you some fast decay, and it actually gives you, if you then use the minimal surface equation, and you actually get even faster decay on the Laplacian function. In any case, the idea is that you can model the minimal surface equation by the Laplacian equation. And so let's just pretend for a moment that, using this fast decay. Decay of the curvature. We can model the minimal surface equation by the Laplacian equation. I still haven't explained to you why we want this power bigger than 2, but this will come next. Right, so we have, right, at the moment, right, we have these coordinates, we have these rho theta coordinates, right? And it's defined now in these coordinates, since I want it to be defined when rho is bigger than 1, right, it's defined in this half plane. Function u is defined in this half plane, and so is W. Now, if we make a conformal change of coordinates, so if if we make a conformal change of coordinates where we are mapping, so we use the coordinates x comma y, where y is theta and x is log of rho. If we use these, this is a conformal change of coordinates. And if we use these coordinates, then in the new coordinates, it's defined in this half space. And you see that if, so had u been actually harmonic, not just satisfying minimal equation, but had it actually been harmonic, right, then the function in these coordinates, then u in these coordinates would also be harmonic, right? So u in these coordinates is u at x comma y, right? The coordinates change is this way, right? If I go the other way, right? It is like a rho is e to the x, right? And theta plus 1. So this here is e to the x times y. And likewise, I define w tilde this. Right, so you see that, so you see that if u is harmonic, then so is u tilde, right, just because it's a conformal change of coordinates, right? And of course, if u is harmonic, then actually w tilde is also harmonic. So that both u and w tilde. By w tilde, right, is now the difference of two harmonic functions. Right? So, right, okay. Now, so that was if it was actually harmonic. But now you see that that's where we need this power better than 2. Because if you make this conformal change, then actually the power 2 go away, and you are left with this other power. And then you have to use also the nonlinearity equation. But in any case, what you get is that when you do this conformal change, you get that the Laplacian of u tilde and actually of w tilde, that this here decayed. So this is what you get after you change this. You get a fast decay of the Laplacian of w tilde. And this comes from this. Together with, you have to use the equation. So this actually gives you, and this is decay fast. Right, but there you, again, you need this power better than 2. And so this gives you that you can model, again, you can model this by the actually harmonic functions. And then you get some error term that you can control because you get this fast decay. So let's just pretend. So this allows you, so this allows us this fast decay allow us to pretend, let's say, that w tilde is harmonic. Now, so let me just really pretend it's harmonic, and then right now it's also embedded, right? The minimum graph is embedded, which means that w didn't change sign, right? So I can assume that, so we can assume that w, so assume that w is positive, right? Hence, so is w tilde. So now you have this positive, so now you have this, so if you're looking at w tilde here, you have this positive harmonic function. It's defined on this half space. And you want to look at how does this vary along the x-axis, right? Well, all you do is that you're looking at now, so you want to look at what is the variation along the x-axis. So you're looking it up in a point here. x, 0. We want to compare it with the value right, so the point in the original coordinates, the point which was 2, 0 is transformed into the point log 2, 0. Right, so you now want to look at what is the difference, what is the ratio of this with the value here of this function W2. Well, if you're looking at this here by the mean value inequality, since I'm now assuming it's harmonic, by the mean value inequality, this is the average, right, over the disk here. This disk here, center x and radius x, right, of W. So, but this function here, right, is not negative. So if you integrate over a smaller set, then you get a smaller number, right? So if I'm integrating here, so this here is certainly bigger or equal to 1 over 2 pi, this is again because W tilde is not negative, then I get here something less if I'm just integrating over this here. I wanted here it to be the boundary, sorry. This here was the boundary. So if I intersect this with a disk of radius 1 centered now at the origin. So, right, so I get something smaller if I just integrate along this piece here. But now, so now by the hierarchy inequality, when I'm looking at this is over like a compact set here. If I had moved it in, I should have shifted in a little bit the ball so that they were away from the boundary. Then by the hierarchy inequality, the value here is more or less the value at each point, right? So by the hierarchy inequality, it's a positive harmonic function. So as long as I was away, a definite amount away from the boundary, then the ratio of the values are bounded. So therefore you see that this here is now bigger or equal to some constant times W tilde at log of 2, 0. And now if you use that x divided by x, right? And so now if you insert, right, that this here is just W in e to x, 0, right? And this here gives you exactly, that is exactly the lower bound. This is exactly the lower bound in the theorem. This is exactly this inequality here. And the upper bound you can get similarly, or you can use an inversion formula. Right? And in fact, all this saying here, in the case of harmonic functions, another way of thinking about this here is just that this is the way that non-negative harmonic functions flow up near the boundary of a disk. So if you have so in any case, this is the variation of the separation as you're moving out. And so this is going to be useful. So now, in fact, what you have is that the lower bound, so the lower bound can be achieved. Right, in this theorem, so this is an example showing that the lower bound, so the lower bound for the separation can be achieved. right? And so, right, in fact, at least if we still pretend that U and W or U tilde and W tilde are harmonic functions, right? Because if I now looking at, suppose that W tilde was the real part of 1 over C, right? If I'm looking at this function here, let's call it B, and W tilde, this is going to then play the role of W tilde, right? So this is defined here in this half space, where X is positive. So if I'm looking at this function, so this function, right, is just this. So this is a non-negative function, and if I'm looking at the value where Y is 0, then this here decay linearly, right? It's decay like 1 over X, right? So it's decay exactly like it was decaying here in these coordinates here, right? This here decay like 1 over X, right? So if I call this B, and now I integrate this function here. So if I now integrate from 0 to Y, B, then you see that, so this here, right, if you're integrating the separation, right, if you have an embedded multivariate graph, and you're adding up the separation, right, between consecutive sheets, then you just get the height, right? So if we're integrating, so it's pretty much the same to integrate the separation. So if I integrate the separation here, well, the function I get is then such arctangent. If I'm integrating here the separation, then all I get is arctangent. Right? This is like summing the separations, right, to get the function back, right? So once you have the separation, you can construct the function back, right, by just adding the separations, right? So now this, if you think about this, right, so how does this look like? So this is now in these coordinates here, in the y, x coordinates, right? So in the row theta coordinates, this function here would then be, right, would be arctangent of theta over log of rho. Right? If you're looking at, so you get this multivariate graph, right? This is a graph, multivariate graph of a harmonic function, right? Because the separation was harmonic and we're just integrating the separation. And then we're making this conformal change back. So if you try to draw this multivariate graph, well, then you see that you get a multivariate graph that lies actually in a slab. So it's like between minus pi half and pi half. And then it's accumulating on the top to this plane here, and it's accumulating in the bottom. But it never quite reached this plane here, and it never quite reached that plane, but it go in, it spiral in asymptotic to it, right? And so this is an example that we don't like, because this here, so now, right, so now the idea here is that if we take this embedded minimal disk, or we're looking at, if you will, a sequence of these. If we had a uniform bound for the curvature, then we could model it all on a fixed small scale depending on just this bound on the curvature, right? Then obviously they would be modeled by graph. So we may assume that the curvature of the sequence blow up, and the idea is that we then want to decompose it into this multivariate graph, and then we want to somehow build back the embedded multivariate graph out of embedded minimal disk out of this multivariate graph we have decomposed it into. If our embedded minimal disk, if part of our embedded minimal disk looks like a multivariate graph like this that spiral into this plane on the top and spiral into that plane on the bottom. And let's say that just as in the helicoid, there are two multivariate graphs that spiral together. So imagine that this was part of the embedded mineral disk, and then there was another multivariate graph that was spiraling together with it. And then imagine also that just like the helicoid, these two multivariate graphs could be connected by just going into the axis and then coming out again on the other multivariate graph. So if it could be somehow connected by somehow short curves, then we would be very unhappy with this picture, because this would be something that was quite different from the helicoid. This sequence here, if this was kind of a limit of a sequence of minimal disk, embedded minimal disk, then there would be like a singularity up here near this plane, and there would be a singularity here, and then there possibly also would be some singularity in the middle, but it wouldn't like convert to something really nice, like a foliation of flat planes. So we want to rule this example out. And so, right, so now this kind of example is now ruled out by using this lower bound for the separation. And the idea, so the idea is like this, right? So this here was an example of a multivariate infinite valued graph, which was a graph of harmonic function. It certainly is very possible that you can construct one infinite valued graph that looks exactly like this, which is a graph of a function satisfying the minimal surface equation. But you're not going to be able to construct it if you also knew that it was part of this big embedded mineral disk, and those two, and there was another multivariate graph just like it that we were spiraling together with, and those two multivariate graphs could be connected. So let me just state this in words. So one to rule out that multivariate graph can accumulate in finite time, let's say finite distance, or maybe just accumulates, let's say, to a plane. Right, so again, the feature here is that you could think about just near this plane. Right? You have this infinite value graph, and it's spiraling into a plane, and we want to rule this out. So we want to rule this out. So we want to rule out that a multivariate graph can accumulate to a plane if this multivariate graph is one half, let's say, one half of an embedded minimal disk, where the two halves can be connected by shortcuts. Right, again, think about this, right? So remember the helicoid. If I took the helicoid, if this here was a helicoid, and I remove the x3 axis, then I get two infinite value graphs. Think about this graph of this function here as one of these two. And think about that there's one just like it that's spiraled together with it. If they were together together with something in the middle where formed a big embedded minimal disk, then we would be very unhappy, right? So this is what we want to rule out, and so we can rule this out. So I don't know if I need it, if I do it. So we can rule this out. By a flux argument. Right, so the idea is that you get something extra from that is part of the big embedded minimal disk. Right? So there's something that is different that didn't happen, that wasn't the case for this multivariate graph. And that is that, yeah. Right, so the picture here is that you have this multivariate graph that line this slab here. Really, you could even restrict yourself to just a neighborhood of this plane above. So this is one half of it. Then there's another multivariate graph that is spying together with it. So it's lying here like this. Those two multivariate graphs that spire together. Right? And then they somehow, in some way, we have no idea how they do, or very little idea a priori how they do. They connect in the middle. But they connect by short curves, meaning just like the curves like in the helicoid. Remember that the helicoid is really like a rule surface, right? So this means that if you have, so if this here is one of the two multivariate graphs, then the other one is just kind of the continuation of that half line, right? So you can connect them by these curves that just go across, right? Right, so see, you see that this, so you can have one of these multivariate graphs. Right? You can have it, at least if it is a graph of a harmonic function. And of course you can have two of them. But the thing is that they couldn't be part of a big minimal disk. And this is, do you see what I mean? Right, I haven't explained why, but right. And now, so now what is the thing that is distinguishing? So this is that the flux, if you're looking at the flux, so what is not the case in this example is that if you're looking at the flux as you're going down one of these spiraling curves here, then the flux is infinite. And if you're looking at these two, so I just have so little time that I just have to somehow give a vague possibility argument. So if you're looking at the flux along this curve that's spiraling down, so this is the flux. It's really like you're looking at the either of the function that's a graph over, or equivalently you're looking at the x3 coordinates, and you're thinking about that this here, since the surface is minimal, that this here is a harmonic function. So now the flux is just the flux along this green curve here. It's just the normal derivative of the x3 function along the curve, along this spiraling curve, which are now like this. So the idea is that if you're looking at this flux here, that this here in this example is infinite, and it may actually still be infinite in a case where it's part of a big embedded minimal disk. But if you sum them together, if you're now looking at the sum, so if you're looking at this here plus, so you have this other curve that we're spiraling together with. If you're adding the fluxes, then it's not anymore infinite. It's actually right, because this here is, and why is it not anymore infinite? Well, it's just because if you're looking at these two curves, this is one of the spiraling curves. It's the yellow one, here's the green spiraling curves. But then you have these short curves that these short curves are these are the short curves that go across. Right? These are the curves where you just continue. If it was a helicoid, you just go along the straight line and you just continue, and you would end up on the other multivariate graph. So, right, so if you're looking at these curves, right, they all together bound a disk. Right? And so now, just because this x3 function is harmonic, because the x3 function is harmonic, you just, by the Stokes theorem, right, these together span a disk, which let's call it D. Here, we span a disk containing this giant embedded minimal disk. So this here is now 0. And then, right, so then the flux along here plus the flux along here is the same up to a sign as the sum of the fluxes here. These here have some fixed bound on the distance, right? So therefore you get that there's a fixed bound for the flux of these. And so this is what is different in this example than in the example if they had been a part of this big giant embedded minimal disk. And so the idea is that using this sort of simple calculation like this, you can now prove that if it was somehow sparring into a plane, you could get a contradiction because you could look at the height and you could prove that eventually, actually, it would have to go below this plane it was assumed to lie above using this kind of flux calculation. I think actually my time is up and I don't have to, I won't be able to find it right. Anyway, so this is going to be used later on in the last lecture to prove, in the end, when we have constructed all these multivariate graphs, to prove that the limit actually have no singularities. No, they're not. Right. So Bill will get into a little bit how they are constructed. So the basic idea is like this: that you get this multivariate graph. As long as you have one point where the curvature is large, then you locate a point where more or less the curvature is maximal. So now you have a point where it's large, and nearby it's not too large. From an intrinsic ball on that scale, you then construct some small multivariate graph. And then Bill will show how one of these extends. And so it is like you have a small intrinsic ball that's kind of crumpled up. And so this small, so the rough idea is that this small intrinsic ball with this huge area have two pieces. It actually, by the boundary, is this curve that's really crumpled up, and it have these two sparring curves in it. And so these two sparring curves are constructed for this kind of blow-up point where the curvature is large. And so the idea is that if you go from one of them, you just go back into the middle of the ball, this intrinsic ball, where it came from, and then you go out, radially out, to another part of this boundary curve, right? So you have this, so it's constructed from this intrinsic ball, which have this huge length, and one of the two parts, so one of the two parts gives rise to the yellow sparring curve, and another part here gives rise to the green sparring curve, and the short curves are just curves that go through the center like this. That's a rough idea.